All right, here's one I wanted to have on the bench for a while, and finally my buddy got a good example of one and sent it my way. It is the Advent Model 300, and you know, this video would be 2 hours long just talking about Henry Close and all of the work that he had done throughout his career. He not only was part of Advent, but he also part of KLH and of course Acoustic Research. And if you look him up, you will see all of the different contributions that Henry Close has made to the audio industry. And among them was this kind of small and insignificant looking receiver. And it's kind of unique. It's nothing super special. It does have a reputation for having a fantastic phono stage, so we're going to look at that. It has a kind of a mediocre amplifier stage, 15 watts per channel, nothing special. And it has not a bad tuner, but a few quirks that we'll talk about in it. And one of the things is this was built to be a good performing receiver to sell for a good price, and it definitely was built to a cost. And I haven't opened this, I haven't even plugged it in or tried it, but I can almost guarantee you it will probably have at least several really bad, if not open, capacitors in it. These were known to have faulty capacitors, capacitors that would fail pretty soon. So I don't know if this thing's been serviced before. I don't know much about it at all, but let's try it out. And of course I'll bring it up on a dim bulb tester and we'll see if we can get any kind of sound out of it. Well, just before we turn it on, just wanted to show you this thing even came with the original owner's manual, which is pretty cool. And what's this? A specification sheet. And I'll show you that. You can stop the video and look it over if you'd like. And it just kind of talks about how it works and how to connect it, everything like that. Flip through it. You get the point. A little interesting. So we can mess around with this later, but you can find copies of this online, I'm sure, to look at. But I thought it was interesting just to make this complete. So this really be good for a collection, you know. All right. Okay, we got it plugged in. Have the dim bulb connected. We're using the 100 watt bulb, 110 watt, whatever it is. Let's turn this on. And the bulb never even glowed. I mean, it's very dim, so that's good. And let's give it a quick check for DC offset, right? So there's nothing there, just 28 millivolts and 42 millivolts there, so that's not going to hurt us one bit. And the breaker's not popped. All is good. So let's move on and connect some speakers and a sound source. Okay, I have the speakers, and let's put this on, turn it on. Ooh, that was a horrible pop. A lot of these don't have speaker protects, so that's what you get. Let's turn up the volume a little bit. Oh my. Okay. One channel's out, the other one is really okay. So both channels are playing a little bit. Yeah. And that's not the pot. That's something electronic. Starting to play. Oh, now it's fading in and working. Both channels. I mean, what part of it is working sounds pretty good. But obviously we have some problems. Might have some leaky transistors. Definitely some bad caps, like I said. So let's open this up and see what it looks like inside. I don't even know. Who knows? Let's get it apart. Put my microphone on here. Screws are now out. Let's take the cover off and see what we have inside. It's always a surprise. And there it is. Lots of wires going everywhere. But that's kind of the way it is, huh? Okay. And you can see, yeah, look at these old caps. These, I don't think these hold up very well, especially the gray and the green ones here. Those, the axial lead ones. If we look at our main filter cap, one of them, it appears to have a hernia on it, so it's probably leaky or getting leaky. And we'll have to take the bottom cover off to see that. But this amp's really well laid out. I mean, if you look here, you have your phono stage over here. You have the main amplifier, and all of this is, you know, just a big heat sink. They're using the whole chassis there as a heat sink. It is a push-pull output. And your tone control and preamp is up here. Bunch of flying wires, but you know, the important ones are all shielded cables. Your whole tuner section is kind of encased in this metal here. The power supply is over here. Very simple power supply. And very interesting. Now these tuners are kind of interesting the way they're made, because they, if you look, they put them together and then they kind of glue down these components in their position like that. That's not an uncommon thing to see in these analog tuners. And then what they do is, this thing is known to have temperature drift. And this actually looks like maybe a little later model of this receiver. But if we look down here, there's two capacitors. Sometimes there's only going to be one capacitor and one of these will be empty. And what these are is they're special. They are temperature compensating capacitors. In other words, most of the time it's desirable to have a ceramic disc cap that has that's NP0 or C0G, which means that as the temperature changes on the capacitor, the capacitance changes. They drift with temperature. That's called a temperature coefficient. These ones purposely have a temperature coefficient. And the reason being is that as this tuner warms up, the circuitry in it, it will drift off frequency. So what they do is they hand pick either one capacitor or a pair of capacitors that do have a temperature coefficient rating of, what is it, N750 or N450. And they'll use combinations of ones that will drift and won't drift and whatever until they get one that tracks with the temperature of the receiver. So you never want to change those. But here's the catch-all. These caps also will fail with moisture. So if you see one of these that came out of a damp environment, these caps could actually fail and they won't drift in the correct manner. And you do need to find another suitable replacement, which could be tricky. And we don't know. This looks pretty clean in here. It doesn't look like it's ever, there's no rust or corrosion or anything. So I have a feeling these ones are all going to be okay. We're not going to touch them. Okay, I unscrewed the bottom cover, and I just wanted to show you this here. Look how clean this thing is. Even on the inside, and look at that. So that really makes me happy. I think this is going to be a very good example of this receiver. So it's definitely going to be worth restoring because the board is in really good shape. It doesn't appear at first glance. You can look around on there. If I bring you in a little closer, you can see there's really no sign that anybody has been working on this at all. So let's go around and let's check the ESR on some of these. I'm predicting we're going to have bad caps, but maybe not. I've said that before and they've all been perfect and it made a liar out of me, so you never know. Okay, I'm doing this to troubleshoot. Okay, I know a lot of you say just go ahead and shotgun it and replace the caps if they're bad, but it's important to go through and check things to see where you are when you start. You don't want to introduce other problems or cover up problems or anything like that. So it's nice to, if you have the time, to spot check it. Again, I'm not doing this for a living. I'm doing this for fun, so I can take all the time I want. So who cares? So let's start with this one. And what is that? 10 microfarads. Getting a little tired. Okay, so these are all... That one's a lot worse. See that? How about these ones over here? Okay. I think I'm in pretty good frame here. Yeah, they're all kind of tired. Now let's look at these gray ones. This is 1 microfarad, but it's not, so it's not going to read. Well, that's about to be expected. About 5 ohms. Not great. Now, how about these ones over here? That one's totally dead. Let's see. Yeah, definitely. That's a dead capacitor. And that one, that's dead too. Those ones are bad. Very bad. How about these? Not too bad. These are 100 microfarad. They're not great, but they're okay. How about this one here? That one's barely reading anything at all. See that? About 20 ohms. That's the same as these ones over here. Let's see this one here. And this one here. That one's real bad. See it? See what I mean? Pretty much, you know, a good percentage of these is pretty bad. If we go over to the tuner section, the tuna, let's see. Reading better than the other ones of the same ones, but still bad. Better yet, that's the most lively one of all the ones on the board of that type. Let's see what our filter caps down here at the bottom look like. Okay, I'll turn this around sideways. Get the meter over here. Let's go on one side. I would expect better than that, but it's okay. And this one's worse, and this is the one that has the hemorrhoid on it. So the main power supply caps are going to need to be replaced too. So this needs a total recap before we do anything else. So yeah, look at that. 1300 nanofarads. So that one's totally bad. Well, that's 1.3 microfarads, isn't it? But, so it's reading a little high. Let's see what this one says. It's dead. Yeah. Wow. That one's really open. That one's bad. So, I don't know. But I'm just going to replace them with these ones that I have. I have these Nichicon Golds. I'm sure they'll work just fine. Alright, as you can see, all the capacitors have been replaced. And before you reach for your caps lock key, like you like to do, and with your little crabby comments, I must remind you that I have 300, approaching 400 videos, and many of them have the solder and chats in them where I actually show you, as I'm talking about things, how to replace capacitors and things. So before you start complaining about how I never show you how to do anything or fix anything, I suggest you look through my many other videos where I show this. I don't have to do this every single time. It's a lot of work to sit here and record replacing capacitors, upload it, and so forth. So with that said, it's all done. Let's see if it works, and then we'll move on from there. And I did end up replacing these filter caps too, and I had these in stock, and they're 4,700 microfarads. They're a little bit bigger, but they should work just fine. So let's see if it works. I have an antenna connected. We're going to try the tuner for the first time and see what we get. Okay, we have sound.
Is it hard to get certified? No. In the lives of everyone.
Wow.
iHeartResults.com. Gilbert worked at 10 million subscriptions sold.
That is one really hot tuner. Down here in the basement, you know, I have an outside antenna, but even where I live, it's very hard to receive FM. And you can see I'm getting stereo and everything. This thing's perfectly aligned. I'm not even going to touch it. That's amazing. And if you noticed, our problem with the sound being all choppy and cutting out is gone. So it was 100% capacitor issues. There's nothing wrong with the transistors or anything, which is a good thing. This receiver is in extremely good condition for its age, so this is going to be a great example, and it's definitely going to be one for the collection, I think. So I think what we're going to do now is make a couple little, at least one little modification, and then we're going to go through the alignment. And then when we're done aligning it, we'll do a test on it, see how it performs, and that'll be that. Now, if you recall at the beginning of the video, we turned the power onto this thing and there was this loud thump. And the reason that there's a loud thump is because, and if I zoom you in a little bit, here's one channel of the power amplifier section, and you can see your outputs, your drivers, your bias circuit, your bias control, your differential input, and a couple things kind of pop out at us right away. First of all, there is no adjustment for DC offset. So you really have to have matched components to make sure that you will have proper DC offset, like especially this differential pair. If they're not well matched, what's going to happen is one is going to be turned on a little bit more than the other, and you always have this DC offset at the speaker terminals. In addition, when you turn this on, all these capacitors and things are charging up, and all these transistors are warming up, and all these things. And until everything kind of settles, you're never going to have a perfectly balanced voltage here at the midpoint of these two transistors. If one of them is biased on more than the other, you'll see extra voltage, either positive going from this up here or negative going from down here. You'll see at the speaker terminals. And if you notice, the speaker terminals are directly connected to this. I mean, this is the speaker select switches, but there is no relay. There's no protect circuit. There's no anything. So any difference in, any offset voltage, DC level that's here is going to go straight to the speakers. So that's what that pop is that you're hearing. And more importantly, what do you think would happen if one of these transistors shorted? If any of you go back and check out my video that I did, I think it was a Kenwood, KR710. The Kenwood KR710. We actually had this situation. The amplifier, when I got it, when it came on the bench, one of these output transistors, and I forget if it was the positive or the negative side, was dead shorted. And that short just connected this DC voltage straight to the speaker. So if I had connected a set of speakers directly to it, I would have burned those speakers up, because there's really no protection for that. And this is the same kind of circuit, same situation. So unless you want to risk putting 22 volts on your expensive speakers, I would suggest making some changes to this to protect it a little bit. So how can we do that? There's a couple ways we can do it. First of all, we can use one of those, modules that you buy on eBay or Amazon or AliExpress or wherever, and the speaker protect modules, and they're really neat because it's just a little board with a relay and a little bit of circuitry, and it monitors things like DC offset and so forth. And if it's not correct, it'll disconnect the speakers from the output. Now, if you don't want to get into something that fancy, which I don't in this little amp, we can always just fit a fuse, a simple fuse right in this line right here. And what that fuse will do is, if you have a direct short, that voltage will put a certain load across your 8 ohm speakers, and it'll cause that fuse to open up and pop. Obviously, you'll get a moment where that voltage will get onto the speakers, but hopefully it won't be there long enough to damage the speakers before that fuse blows. And that's really the key to it, is if we're going to put a fuse in there, we have to determine what size we want to do. Okay, here's a little sheet that I have. It's a cheat sheet, and we're going to talk about another method of figuring this out, but you can download this, and I don't even remember where I got it. I have it on my hard drive, and I just printed it out, but this definitely exists online. You can download it, and all it is a speaker fusing chart. And what you do is you look at, first of all, you figure what speaker impedance you're using. So for instance, we're using an 8 ohm speaker, and then you figure out whatever the wattage rating of the amplifier is. So the maximum wattage of this is somewhere around 18 watts. I think it's 15 watts per channel, full field, but at 1 kilohertz it's about 18 watts per channel. So if you take 18, what they're saying is you multiply that by 4. So 18 watts times 4 would be 72, which would be 4 times your wattage rating. And what you do is you take 8 ohm speaker right there, line it up with 72, which is right around this 70 range, right around here, right? And wherever it intersects the line, which is right here, that's the size of fuse you're supposed to use. So you can see in our instance, it would be a 1.5 amp fuse. Now, another way to do it, kind of the long way around, would be to look at your amplifier circuit. And if you notice, our voltage is 22 volts. So if this shorts out, it would put either positive, and it doesn't matter what polarity is, if it's positive or negative. If this shorts, you're going to get 22 volts with reference to ground there. And so if we take 22 volts, divided by our 8 ohm load, that's going to be about a 2.75 amp signal. So you'll have about 2 amps on there, and that's with a dead short, okay? So you want that to blow that fuse, not immediately, but relatively quickly. And if we go with our wattage rating, remember this is a, would we say it was 18 watts per channel? Okay, we were saying at 1 kilohertz. So if we take our 18 watts, right, and we times it by 8, and then we take the square root of that, it shows that you're going to have around 12 volts when the amplifier is working properly. Okay, 12 volts RMS, which would be the same as 12 volts DC. And if we divide that by our 8 ohm load, 1.5 amps. Isn't that pretty amazing how the how the math works out? So to recap what we're doing again, you take your wattage, which is 18 watts, and you times it by 8 ohms, right? And then you take the square root of that, 8 ohms is your speaker load. If you had a 4 ohm speaker load, you would times it by 4, right? And then divide that by your speaker impedance again. There's your number in amps. Okay? So we know we need a 1.5 amp fuse. Now what I'm going to do here, move this out of the way for a minute, is I'm going to mount one of these fuse blocks inside here somewhere. And a convenient place is these 2 screw holes that are holding the heat sink to the heat spreader here to the chassis. And what I can do is just remove this screw and this screw here. Let's move it into so you can see better. And I'm just going to mount one fuse holder here, and I'm going to mount the other fuse holder here. Or I may have to go here and here because they might be so close together. Let's see. Yeah, I don't want them to touch. So I'll put one here and one here. And that gives us plenty of room. And it's a very convenient design on this amplifier because those will be out of the way. You can still work on the amplifier. You have one wire coming here and one wire coming out here. And as you can see, I don't know if you can read that, but it says out. So right here, you can see right there it says out. That's the output. And it goes directly to the speaker switches. Okay, so let me get this installed. And the first thing I'm going to do is I'll remove one of these screws. And these are sheet metal screws, which aren't going to work for this because we don't want this to work loose. So you can see those are sheet metal. And these just so happen to be the same diameter, roughly, as a 632 screw. So what I'm going to do is I'm just going to take one of these drill mounted taps. I'm going to put it in a screwdriver so I can reach, and I'm just going to tap this out very carefully to a 632 thread. Now I don't want little shavings to go into my amplifier. So what I'm going to do is I'm going to just put some paper towel under here to catch this stuff, just in case. All right. Probably not going to be much, if any, shavings at all, but just in case you want to do that. And then we can always vacuum it out afterwards. So I'm just going to crank this through here like so. And it's just as easy as that. All right, I'm going to take that back out. And this is very soft aluminum here, so you really don't have to use cutting oil or anything like that. All right, and we didn't really even have anything come out of there. And then we're going to take our screw and put it into our little block. And I just had these fuse blocks. You can use whatever you have, but this is what I had sitting around. I have a bunch of these. I got them at a surplus place at some point in time in history. I don't remember when, but so we're going to put this in there. And I'm not going to over tighten it because I'm just going to bring it nice and snug. And then I have one of these little nuts with a lock washer attached to it. And I'm going to run it in from this side. And you can even, if you really want to be fancy, you could put a little bit of thread locker on it, but I don't think that's going to be necessary. And I'm just going to hold this like this. And then I'm going to tighten this down. Like that. And that makes a nice solid connection there. And then I'm going to do the other side right here, and I'll be right back. Okay, we added our wires here, and we have our 1.5 amp fuses. We'll pop those in, and those are going to be really easy to get to if they ever need to be changed. So right up in front there. And we can even make a little label stating what they are. Okay, we'll get the label printer, and we just print out a tag just so people know what size that fuse is if they ever, of course they could just look at what the old one was, couldn't they? But this will give everybody an idea. And plus it'll make it look like it should be there. There we go. Okay. Now then, that's much better. Now we know if this dead shorts, your speakers will at least have a little bit of a fighting chance now, huh? Okay, let's make sure things still work. As it gets later in the day, the reception gets a little bit worse. All right, it still works. Of course, I can tell I lost a little bit of musical fidelity by putting those fuses in there. Never mind. Okay, so I think we're good to go here. Now we can start checking the alignment. Now, if you remember in the schematics, well, let's just look. The amplifier has, as you can see, a bias adjustment. And for this, the procedure on this one is they want you to go across R331 to 333. So you're going to put your meter from here to here. So from just between the two collectors is what you're essentially doing. And they make it really convenient on this amplifier. So you can see those resistors are right here. And they're, well, they 0.15 ohm. And all we're going to do is we're going to connect from this end to this end. And you can put the positive and negative wherever you want. It's just that one way it'll read positive voltage, the other negative. But really, we just want to know what the absolute value is here. We want to know the voltage difference between, across that resistor, or the drop across the resistor. So we have that. Let's turn our meter onto millivolts. And what they're saying is when this thing stabilizes, you should see exactly 3 millivolts. That's a tiny amount. And they actually specify in the manual that they want you to use, they actually mention a model of HP VTVM, Hewlett-Packard VTVM. The reason they want you to use a VTVM is they want a very high impedance meter. They don't want you to put a volt-ohm meter across it because the burden load of a voltmeter may affect this because you're dealing with such tiny voltages. So, long story short, your digital multimeter is ideal for this, and you set it to the millivolts mode, and we can turn this on, and we'll just wait and see. I'm going to set it to auxiliary so there's no signal, and you can see it's high right now, but don't adjust it right away because you have to wait until the amplifier settles down a little bit. Right now, what you're seeing is the transistors are actually coming up to temperature. Now, eventually this will settle down, and then we're going to set it. And what we want to set it for is 3 millivolts, and we're going to do that by adjusting this potentiometer right here, and this one for the other channel. So we're just going to wait, and you can see it's creeping up right now. hopefully it'll drop back down as soon as the transistors all come up to temperature. But I'm going to wait about 15 minutes before I do anything, and then wait to see what happens. Okay, I think that's about all it's going to go now. So let's go on to the bias adjustment pot. And I'm just using this long fiberglass tweaker so it's easy to reach through there. And I'm just going to turn this until I get 3 millivolts. Right there. And you can see it's dropping. You kind of have to wait for the, the bias tracking transistors, to catch up to it. So you make a little adjustment, and then you wait, and then you make another little adjustment, and you wait. We're just going to keep adjusting it until we get it just right. It's kind of hard to stand around the camera and do this, but, well, we'll see. There we go. Okay. And I think that's close enough there. That's pretty good. And it's just going to move around right there. So now let's move it over to this side and see where it's settled. And I'll go up just a wee little bit. And again, if you've watched many of my videos, if anything, I'll bias these amps a wee little bit on the cold side because usually you're just trying to keep away the any kind of crossover distortion. But most of these amps, they err on the side of caution. They have you bias them actually hotter than they need to be because usually the transistors they use are better matched than they assume. They're just setting it up for worst case scenario. So that's good. And like I said, I mean, when you're dealing with 1 millivolt, yeah. So that's it. The bias is set, and that's all you can do with this amplifier. There's nothing you can do about the DC offset other than replace transistors if it's that far out. Okay, the next thing we want to check is our plus and minus 15 volt supply. And on the later models, which this one is, the 15 volt regulator is right here on the heatsink next to the outputs. On the older models, there will be a separate little board that will have that transistor or that voltage regulator on it. And we want to look at the pin on the right. This is called RA400, and I'm going to just measure that with reference to ground. And I should see 15 volts plus or minus like 10% or so. So we're going to go here. And there it is, 15 volts. Then if we go back over here and we look at this pin right here, it's right there. Oh, my finger's in the way. It goes to this wire, which is the muting switch. And if I touch this right here, I should see my negative 15 volts. And there it is. So our 15 volt supplies are good. Now what we just checked was our plus 15 volt regulator and our minus 15 volt regulator right here. And we also have a plus and minus 12. And that's going to be Q111 and Q110. We want to look at the emitter of Q110 and we want to look at the emitter of Q111. So those are over here. Let's see if I can get everything in shot here. And that's these little transistors here. This is Q110, this is Q111. If we go to the emitter, we have 11 volts. And if we go to the emitter of this one, wrong emitter, other emitter. Okay, 11 volts. So it's exactly 11 volts on each side, positive and negative. So it's not plus and minus 12, it's plus and minus 11 on this one. And that's probably has to do with these Zener diodes and everything. But they are very well matched. So I'm inclined to not mess with it. I think we'll be just fine. Okay, let's do a quick test of the phono stage. Now, this is not going to comprehensively tell you exactly if this thing is reproducing the RIAA equalization curve perfectly, but it's going to really give you a good idea of how close you are. Let's take a look at something here. So to understand this a little better, let's look at this chart. What this represents is the equalization curve that you add to a phonograph stage. And this was created many years ago and is still used today with vinyl records. A record doesn't record frequencies all the same way. So in other words, what I mean is, if I put a certain amplitude of signal onto the record when I record it, and then I go to a low frequency versus a high frequency, 20 hertz versus 20 kilohertz, you'll find that when you go to play the record back, it won't play back in the same levels that you recorded it in. And it's because of the physical limitations of how the stylus tracks inside the groove and how the cartridge picks up that sound. So you have to compensate for that. So what they do is, when you record the record, you actually reduce the bass notes a lot. You reduce the low frequencies and you crank up the high frequencies. And that's going to cause an unbalanced sound, okay, that's going to sound very tinny when you play it back just as is. But if you do the opposite when you play it back, you boost the bass and reduce the treble, it'll actually flatten it out. I know that sounds strange, but it all has to do with the mechanical nature of a record player, of the cartridge, and of the stylus that tracks inside that groove. So I talk about this in other videos. You can go check it out. But bottom line is, we want to test that. And there is a format that is used that everybody follows, and it's this curve right here. This red line is exactly the type of frequency shift, or compensation, the amplitude compensation versus frequency, that this phono stage has to apply. So what that means is the crisscross point, your flat point, where it's 0 dB, where it's your original signal, is going to be a 1 kilohertz. So let's just keep it simple. If I have a 10 millivolt signal here, then it's at 20 hertz, which is the lowest frequency, it should be 20 dB higher, which means 20 dB is going to be 10 times. So I should see, if I have 10 millivolts here, I should have 100 millivolts here. And conversely, when I run the frequency up to 20 kilohertz, I should see 1 millivolt come out. So 10 millivolts, 1 millivolts, 100 millivolts. And you can see it's not a straight line, so there is some curvature to it, but again, it has to do with the way that a phono cartridge and stylus work. But bottom line, if we check these 3 points and they're pretty much on, then you can be assured that this curve is at least going to be somewhere in the ballpark of where it needs to be. For the average person on the average listening speakers and so forth, even if this were a straight line here, it would sound pretty close, although this is the correct curve for it. All right, so again, with the same amplitude in and just changing the frequencies, we should see the amplitude at the output change. All right, so what I've done was I take my signal generator, and you can see it right up here with all the light glaring off of it. And I'm coming out of the signal generator, and I'm going down into the phono input right here. All right. Then I'm coming out of the record out jacks of the amplifier and into my oscilloscope right here. You can see that. And if you look right here, I am now driving. The average magnetic phono cartridge goes anywhere from 3 to 6 millivolts output. So I have a 6 millivolt signal driving into there right now. And that 6 millivolt signal at 1 kilohertz, okay? So we're checking right here. all right, 1 millivolt, or 6 millivolts, is giving an output at the record jacks of 300 millivolts roughly. See that? 300 millivolts RMS. And you can see the signal's jumping around because it's a tiny signal going in and everything, so we have a little bit of noise, but don't worry about that. So what we should see is 10 times that output, or 3 volts when we go down to 20 hertz. So if I go down to 20 hertz, see how big the signal gets? Let's bring it in here. Okay, and I actually have to change the scaling of the scope. And you can see I have 2.77 volts. And we said that we wanted about 3 volts, so it's a little bit off, but generally we're pretty close to where we want to be. And remember, the frequency response of this stereo is not exactly 20 hertz to 20 kilohertz. So I would say that that's working properly. And if we go up to 20 kilohertz, see how tiny it gets? Now we should see 30 millivolts instead of 300 millivolts. So if I turn the scale up again, and I move all this, you can see it's very jumpy. But if you read it right there, there's your 30 millivolts. Okay? So what that tells us, just in 3 little set points, we pretty much have a good idea that our equalization curve and our phono stage is working the way it's supposed to. Now you can get crazy and you can do a Bode plot and you can do all kinds of other more complex measurements to verify the exact shape of the curve. And I did that actually on other videos. I showed it. But for all intents and purposes, this is really all you need to do, is to do it this way. So that's it. And again, we go back to 1 kilohertz. And we change our scale once again. And you can see back to 300 millivolts. Okay, so that's it. Just you basically 1 kilohertz should be the one output, and then at 20 hertz it should be 10 times more than what it was at 1 kilohertz, and at 20 kilohertz it should be 10 times less, or 1/10 of what it was at 1 kilohertz. And that's your RIAA curve, and that tests your phono stage. Quick and easy. Okay, let's see if we can do something with this tuner right now. As you remember from earlier in the video, the sensitivity and selectivity is fantastic on this. I don't want to touch that. But one thing I did notice is with the tuner perfectly on center of the channel, you can see both of these lights are supposed to be lit up, indicating that you're on center. But as you can see, it's showing that it's off. And usually when that happens, that's a result of your detector circuit being out of alignment. So we're going to go ahead and align the detector. Now, we're going to follow the instructions because it's kind of unique how they do it. So let's do it that way. Okay, we have a little bit of a problem with my idea, because to do the detector alignment the way they want, they actually have you adjusting they want you to short the junction of R625 and 626 to ground. And 625 and 626 on my unit, which is a newer one, is there's 626, there's 625. And if you look on the diagram that they have, it's a good bit different. You can see this 625 and 626 are not there. So I have a feeling that this isn't going to work this way. And you can see the stereo light, all that stuff is just in different place. Some of it is similar, like the actual R707 that you're going to adjust is over there. That hasn't moved. But this part of it appears to have been changed. So we are not going to do that. I'm going to use my signal generator. And what I'm going to do is I'm going to turn the tuner on. I'm going to let it warm up so there's no drift. And I'm going to center the channel. So I'll tune this until it's centered on the channel. And I'll do that by adjusting this while using my scope. And the scope is just connected once again to the tape monitor outputs. Okay, and we're going to use this scope this time just because, you know, to mix it up a little bit. So I'm going to tune the tuning dial. And there it is. I'm right on. And you can see it's a little bit touchy. So right there, we're right on. Okay, so we're right on center channel now, and I'm going to reduce the signal till I just get a little bit of noise. Not that much noise. Right there, see that? So we still are a little bit off center. So we're going to move it ever so slightly the other way. And what we want is we want just, you see that? Now there's a little bit of noise here and a little bit of noise here. That's what we want. We're right dead center of the channel. Now what I'm going to do is, now that we're centered, I'm going to go down here. And you can see this, and there's R700. We're going to take an alignment tool, and we're just going to adjust this, hopefully, until we get a tuning light. You see that? We want them to both be equal. So right there, that looks dead on. Okay, this metering circuit isn't the greatest in the world. It doesn't really go, you know, it barely toggles a little bit because these red LEDs don't really make a big change with little changes in voltage, and that's a problem. So what I ended up doing was, if you look at the way this is made, for both of them, so here's the meter circuit, and you can see your two LEDs, they're both tied to your plus 15 volts. So that's what at H&L, they both tie together and go over to here, to a 15 volt pin. And what I decided to do was, if these are both equal in voltage between here and here, then the two LEDs are balanced. So what I did was I put a null meter in between these and then set the pot here until there was 0 volts between them when I'm on station. So let me demonstrate that. So I just have, this is a fantastic meter, this Sanwa EM7000. It's an FET meter. It has the same kind of an input impedance as a VTVM, but it's battery operated. It has this really cool null mode, and it has a very low voltage range that you can adjust. And that's kind of where I am right now. I'm on the 0.3 volt range, so it's plus and minus 150 millivolts from center. So what happens is, first of all, as you can see, I'm right on center channel. Okay, and what I did was, by adjusting this pot for null, it makes both of the LEDs have equal light. See how if I turn it that way, it goes off that direction. If I turn it that way, it goes off that direction. And if I just center it, I don't even have to look at the LEDs. I can look at the meter. And then when I look at the LEDs, since my eyes can't always tell from the angle that you're staring at them, they're both the same brightness. Now, also, if I go off channel, if I go one way, the voltage drops that way. If I go the other way, see, it kind of goes off the other way. Let's see there. And if we just center it, we're right on center channel, and look up here, there we are. Now the only problem is this is more of a gimmick than anything else. They don't really toggle very brightly when you get over top of a station. It's not very sensitive. So not very practical, but it's set. Now as far as dial accuracy is concerned, we're right on 98, and I'm set at 98.1, so it's right on. So we don't have any problems there. And if I go here, I have everything set up properly. So right now I am putting 15 microvolts into the tuner, and I can go all the way down to 3 microvolts, and I'm still getting a signal at 3 microvolts, and even down to 2.5 microvolts you can just barely see the waveform, and you can get a listenable with static at about 5 microvolts. If I go into stereo mode, okay, I'm not getting a stereo pilot tone, but I can tell you at 5 microvolts that's listenable. And if I go up just a little bit more, I'll let you know right there at 9 microvolts we are just barely starting to get a stereo signal. You can see it is flickering a little bit. And I bet if I go up to 10 microvolts, no, not quite, it's staying on pretty close, but about 15 microvolts. There we go. 15 microvolts, that stays in solid stereo. So this thing is very sensitive. It's, the selectivity is good. I think the only problem is these lights, and it just depends on what angle you're looking at them as to whether they're set or not. But the tuner is working, and it's working great. Unfortunately, this is a completely different board from the service manual that I have for this. There's 2 different versions of this. There's one, I think they're calling it the ceramic filter tuner, and there's a different one. There's the other one, which is this one. This one has a whole bunch of adjustments on it, and this one does not. This one's using all integrated circuits for the IF and with filters. This one has discrete IF. Well, actually it does have the little chips in there, but there's discrete cans for each one, and there are no ceramic filters. They're actually using these IF cans for the filters. So not exactly the same, but it's a good tuner. Can't complain. Okay, now for the fun part. Let's check the amplifier section. I have a 1 kilohertz signal at 500 millivolts RMS going into the auxiliary input, and I have the 8 ohm dummy load connected, and you can see on this scope at the tape outs we have a very clear, clean signal. And what we should see is before clipping, this should do about 18 watts per channel at 1 kilohertz, and it should do 15 watts per channel at 20 hertz to 20 kilohertz, full bandwidth. So let's turn this up, and what we're looking for is we are looking for right there, we want to see somewhere around that 12 volt mark, remember? So let's look at that before clipping. And right there's clipping. If I bring it down, okay, right there is the edge of clipping, and we're right about 12 volts right there. And remember, 12 volts squared is 144, right? Divided by 8, 18 watts right on the button. So this thing is dead on with its spec. Okay, now right there we're sitting at our 18 watts per channel, and if we go over to the harmonic distortion meter, 0.07%, so that is a lot better than they were saying. They were saying somewhere around would they say 0.3%? This is not 0.08%. It's climbing up as the amp gets hotter. And it's just getting warm to the touch. I mean, it's not getting hot at all. So I think we're good. It looks good. All right, so let's now go through some different frequencies here. And let's try 20 hertz, of course. Well, this amp bottoms out at 40 hertz according to the specs. So let's do that first to make sure it can meet that spec. And I will adjust the scope. I have to move the camera for a minute. And 40 hertz looks really good. And we're not quite getting our 12 volts, just about. So there's a little bit of drop off. And you can see, driving this thing hard, we're about 0.5% THD at 40 hertz. And if I go down to 20 hertz, I bet it's going to really drop off a lot. Well, no, it looks good. It looks really good. Okay, our amplitude did drop a little bit. We can, yeah, you can't really bring it up there. It'll start to notch, you see it? But you're getting some distortion. So, not bad. Now, again, I have this set to the 5th harmonic, and I'm A-weighted distortion measurement, so it's 1%. But, again, I think we're good. Now let's go to 20 kilohertz. Let's see if we can straighten our... That actually looks really good. Take it just a little bit down. That's actually a little bit high. So let me take it down to that. I'm getting 18 watts almost across the board, believe it or not, with pretty good distortion. And my distortion meter is not reading right now because it's out of range. I'd have to reset some of the settings on this. But you can see how clean that sine wave is. So the amplifier is fantastic. We just done no problem with that at all. Okay, now for our little test. Time to do stranger danger like we do on most of our amp videos. See what it sounds like. Hear what it sounds like. Well, I would say that's a pass. Sounds really good. Now we know everything works good. And wow, now it kind of makes me want to get the matching turntable to go with this. Advent made a really good turntable to go with this phono stage, and I guess the pair sounded really good together. Of course, then you have to get a set of large Advent speakers to go with it, or a set of ARs. And even the smaller Advent, and have a set. But you know, for a little 15-watt receiver, I think it performs pretty well. And remember, I was checking it around that 12 volts, even down at 20 hertz, and it still was hanging in there. So it can outperform its specs just a little bit. And remember, we didn't change any transistors or anything, just a recap is all we did, and touched up the bias. So, fun project, and I think this is ready to go into use, and I have plenty of other projects coming up, believe it or not. I have a ton. So I'm not sure which one I want to do next. I think it is, well, it's going to be a large project is what I'm thinking I'm going to do next. And so I'll leave that just at that. So anyway, until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Thanks. Bye-bye.